This is, for instance, one boundary. So how many boundaries has this one? One. What about this one? 5. So these are the 5, you know. What about this one? This is homework. You can take a picture with your phone and think about it. That's not totally a joke. So here we have more surfaces. These are all with boundary. And of course, you know, I'm picturing very simple examples, but you can imagine, you know, by the complexity of this, you know, they don't have to have this beautiful symmetry, but they can be very, very wild objects. You know, if you can picture all the possible surfaces we have, you have an amazing mind. And here are more surfaces. These are quite interesting, you know. Innovation knots, I don't work on knot theory, but there are certain things of knots I really enjoy. So what I like is surfaces whose boundary is a certain knot. I mean, in the previous surfaces, in the previous surfaces, the boundaries are quite simple. They sit, you know, in our space as a circle, not twisted, nothing. Here, it's quite different. You know, this is, if you know a little bit of knot, this is the boundary of this surface is a trefoil knot. There's 3 twists. And this boundary of this surface is also that same trefoil knot. These are 2 different surfaces. You can pass it around, I've made a surface whose boundary, this is it, is a trefoil knot. Oops, sorry. My pointer goes backwards. The backwards key goes forward and vice versa, so you'll have interesting things. So one feature one could study in surfaces is the orientation. So we can say a surface is orientable if we can put a Möbius band. A Möbius band is this figure. There's a little, the ants are moving. That's the whole point of this talk. The ants move. Oh, there it is. So this is an Escher painting. This surface, if I paint it, you can see it in this little demonstration. I could paint it, and I will go to both sides. If it is made of paper, I will go to both sides of the papers without lifting my pen. So we said it has only one side. And you can move, you know, through the whole paper, the 2 sides. And again, if I grab a band, twist it, and glue it, I can do that. So this is a non-orientable surface. And here again is the, and this is the Klein bottle, which is another non-orientable surface. Oh, I have one. This is a surface that we can't really build in R3. Here it is. This is like a projection, the shadow of the surface. In the same way that when you have, say, here a line that goes on forever and 2 points. Well, in the blackboard, I can't go from this point to this point without crossing this line. But if I have one more dimension, I can. Well, in the same way, we cannot construct an honest Klein bubble in our 3-dimensional space. So, you know, we do this picture that represents, with self-intersection, that represents the object that does not have self-intersection. That, my model, is not really a surface because it has a crossing. There's a point where 4 walls of my objects come together. That's not a surface. A surface should be always, if you look at a little disk, a little around each point, it should be a flat thing, like a plane. But I'm going to concentrate now in orientable surfaces. And we have one of the beautiful things, my favorite things in life, a theorem of classification of surfaces. So maybe I should ask for you to think for a second if all the possible surfaces, you know, with all their variety that we can have, say orientable. And now, you know, we can prove that in fact, whatever surface, no matter how crazy it is one of this list. So what is this list? Well, this list is like a grid. So if your surface, If an orientable surface has no boundary, then you can deform it into a sphere, or the skin of a bagel, or a double bagel, or a triple bagel, or a quadruple, and so on. If it has one boundary, you can deform it into a disk, or a bagel, with somebody ate a bite, or a bagel somebody ate 2 bites, and so on. And then you can keep going. You add boundaries, and then this is a classification. This is the thing that we are always looking for in math. We made this definition. It's an abstract definition. What is a surface? But then we can produce this very beautiful list, and then each surface that you can imagine is one of those lists. So it's determined by how many bagels you have to glue to make it, and how many holes, how many bites you took out of your surface. So I know you're not mathematicians, maybe most of you, but should appreciate the beauty of this. Just imagine you're a mathematician and think, how wonderful it is to define an object and say, OK, we can. So all these wild surfaces, they belong to one of these. OK, so now I'm going to make a little problem. So this is Augustus Moebius, whose son, I just learned this distressing fact. He has a son who was a famous neurologist, and he wrote a book which was popular at the time called something about the weak mind of women. And he justified why women are inferior. And he was apparently good as neurobiologist, except for certain bias. But anyway, so he proposed this problem in a class. He said there's a king in India, had 5 sons, and he said they have to divide the land, but he wanted every son to be able to visit each other without touching the other son's land. So the regions divided, they don't have to have the same shape or the same size even, but they should share an edge, every region. So the question is, how can you divide the land? So let's look at this problem in the sphere. What is the maximum regions you can put in the sphere? Suppose that the land of this man is a sphere, so that every pair of regions share an edge. So can you put 2 regions divided in 2 countries? Yes, we all know. What about 3? Yes, how? You have to stand behind your words. Anybody can say it? Yeah.
South of the equator, for example, and the two halves of the northern hemisphere.
Right. So if I divide exactly like this is one region, and then I divide the north hemisphere in 2, and I attach it, we are good. What about 4? Can we do 4? Yes, how?
I think it's been the same process. One whole hemisphere, and this one's divided in 2, and one of those halves is divided in 2. Am I missing one?
I could do it differently. I would have the sphere cut in half and then.
Yeah, well, that's easy to see. I mean, yeah. So you cut in half each hemisphere. Of course, if I attach it like this, if I break it as the pieces of an orange is not good, but if I do a little twist, then it's good. Can we do 5? We can stay the whole hour. No. You might have heard about the 4-color theorem or the 4-color problem, which says that every map can be colored with at most 4 colors, of course with the condition that every contiguous country has to have different colors. That's the way we colored. And this is something that was observed by cartographers in the 1800s, but we mathematicians just managed to prove it in the 1970s, late 70s, and the proof was by computers. There were about 2,000-something cases analyzed by a computer. So it's a different problem. The 4-color problem is you need a color that will work for every map. Here I'm asking is, do you have a specific map with a certain property? But if we had a map of 5 regions so that every pair of regions share an edge, we would need 5 colors for that map. So we know that since the 4-color theorem works, this map cannot exist. Okay, so now what about a bagel? So the fact that a bagel has this, it's not a hole, it has this, we call it genus, gives it much more freedom, because any map that I had in the sphere, or any flat map, I have a torus somewhere here. If I have a map, here I have the picture of my map in my hand. I just glue it like this, and if I had 4 regions here, I extend the colors and I have 4 regions here. But I have more way to play around. So in fact, one can prove that in the torus, the maximum number is 7. And here, I made it 7. These are 7 colors. They are rectangles, but these are rectangles that they are secretly hexagons. Each rectangle touches the other 6. And if you go around, there's one rectangle. Here it touches 2, and then it has 2 neighbors. I have a better way. One way to see it is, so here is the before I fold it. You first organize the rectangles in this cylinder, and then I'm going to fold the cylinder and glue the top with the bottom with a twist. That's the usual way to make a bagel. But I have to do it in such a way that the top here will touch the appropriate colors here. So anyway, you can pass this around. Now what if I have a double bagel? What is the maximum number of regions? Well, that's hard to figure it out. Here was 7. This is 8. I did it again. So every region, touches the other 7 in an edge. So you can check it, but many people checked it before. Nobody found it was wrong. And for the pretzel, we call it genus 3. The number of regions is 8. So this takes some work to prove. Here is 8. If you have 4 bagels attached, it's 9. Then 10. For 6 is 11. For 7 is 12. What do you think is 8? Oops. No. This is a trick question. So one would expect is 13, but in fact, it's 12. And the number, G here is the number of tori or bagels that we are attaching. This is the number. Of course, this is the smallest integer, no, the largest integer that is smaller than this number. This is the number for this. And the proof is not hard. If you want to stay a little over, we can do it. I mean, you have to accept one little topology, but this is what topology can do. Okay, so since we are I'm going to make a little parenthesis about women in science. I've been reading a lot about women in science and the problem, and I just want to make my little preaching using that I have a captive audience. So I was thinking about women, and sometimes it turns out that you're looking for a certain women scientist and you don't see it, because when we are so associated that a scientist has to be a man that sometimes when there's a woman scientist, we just don't think of this person, when we're looking for somebody. So I was for another purpose, trying to illustrate this, and I Googled invisible man. I was Googling invisible man, invisible women. This is what you get, the images you get in Google. Now, if you Google invisible woman, you get this. I'm not making it up, okay? This is a picture of my screen. So this is what we are, part of the things we are against, like if this is the idea of a woman, then we have a long way to go. Okay, so let's back to stop the preaching. That's it, no more. Now I'm going to study surfaces. This is a particular surfaces we topologists call the pair of pants. Sorry, let me get my phone. I need to get the time. Come on with time. Is there a clock in the room over there? Oh, okay. Oh gosh, time goes fast when I'm having fun. So this surface is called a pair of pants, you know, for a very, I don't know, deformed person. This is the waist, and here are the two legs. And this is another incarnation from the topology point of view of this surface. Now imagine that I grab, say, the waist, and I stretch it a lot until I make it flat, so it's going to look like the orange surface. And one way to study the surface combinatorially is by cutting. So I'm going to cut the surface, but my cut has certain properties. The cut has to go from a boundary component to another or to itself. It cannot divide the surface into two pieces. And of course, it doesn't have to intersect other cuts. So here I cut the surface in both ways, and then you cut and you open up, and you open up, and you get this shape here. So this is a surface, but now I know that I have to glue this with this and this with this. You know, I label the edges that I cut, and I have to keep the memory that I cut them. And then we have to abstract. We have to take the words. I label, you know, A, and for a certain reason, I put capital A. You'll see Y letter. Capital B, B. For me, since I use a lot of the computer, in math we use A bar or A inverse, but go and put that in the computer. So capital A means A inverse. So this, you know, reading this label cyclically is what we call a surface word. And this word here is like it's a cyclic word. The ring of letters captures all the topological properties of my surfaces, provided that, of course, you tell me how to reconstruct. I have to have this way of reconstructing, you know. Once you have a 4-letter word, you get an octagon, you label every other edge, and you glue, and you get your surface. But all the information is here. Now, sorry. Let's do another surface. So this is a torus, or bagel with one hole. So we cut it. Here we have only one boundary component. We can always do that. Cut it so we get a flat thing. So we cut, we open up, and then again, you know, if we glue this with this and this with this, you get the torus. Now, if you want to play,
when you're doing the gluing, but you have a choice of which way.
Very good. You have, but then you have to tell. We are working on orientable surfaces, so you have to glue. In fact, you can glue with no twist, but for a topological point of view, you can do an even number of twists, and it will be the same. Now here I have, this has a little boundary here. This is a torus. You know, I have a zip, so I open up. I don't know if you can see, it's a torus. It's like I open up. I'll pass it around. This is one of my favorite toys. And then I open up. Oops. And ta-da, this is a rectangle. Here are the corners. So when I glue this and this, I get the torus. It's a nice trick one could do, but time is finite, so these are the two surface words. Notice that these two surfaces that are different, they have different surface words. I mean, of course, if I exchange A by B, you know, get the same word, you know, we can do silly things, but these are essentially different. And also I have these are something that shows how different they are. My two surfaces again. And here, this is the skeleton. There's a figure 8, you know, in dark purple here, and there's a figure 8 here. This is a torus. If you can see, in this surface, I can attach a disk and close it and get a torus or a. So this is the torus with one boundary component. This is a pair of pants. Now the figure 8 in the torus with the boundary component is like an 8. But I have to attach it like this. In the pants, I have to attach it like this. And that makes all the difference later of how the curves intersect. I'll get to that. And this is a beautiful picture. You know, Jos Liss is a retired engineer who I think is a mathematician in his soul, who showed this is for the closed surfaces. You have a certain octagon that you're going to glue pairs of edges, certain pairs of edges. And you can see, you will see how you get a genus 2 surface or a two bagel attached. He has a lot of work of this kind where it helps us visualize of this mathematics. Remember, this is an octagon, and we're just doing topological move, the forming, shrinking without cutting or breaking. And it's almost there. Always make me happy. Gosh. But again, remember, it started with an octagon and certain pairs of edges that you have to glue. Here we're gluing without twist, but because we are in R3. Okay, so now let's study curves on surfaces. So basically, we think of a curve on a surface is, now the surface is going to be fixed, no moved. And we're going to think of a curve. This is a rubber band, but it should be an infinitely thin rubber band or a loop that goes around the surface. So here I have some examples. It's like a circle that I place on the surface in a certain way. And in the same way that we study surfaces up to the formation, now we're going to study curves up to the formation. So now we're going to say two curves are equivalent to the other if we can deform one into the other. So this red curve, this very primitive animation I made, is moving through all the deformation class, not all. Some of the deformation, some members of the deformation class of that curve. Now this is, this type of deformation is different than the surface deformation. Now, surface is fixed, and we allow the curves to move there. Surface, doesn't move. So, how are we going to study the curves, say, in this torus with one boundary component? So here we have a curve in purple, and secretly, I want to study the crossings of this curve. I want to describe them combinatorially. So here I have, that's my pointer, here. Here, this is the same curve, although I made it straight. Topology allows me to do that, just because it's just deforming. And I choose a special representative of this deformation class. I request, that it doesn't do silly things like enter through here, coming back, and going back. I made a curve tight and efficient, so I don't do extra things. So the way we study this combinatorially is by assigning a curve word. So how do I get a curve word? I have my 4 label edges where my curve can land. So I start at any point, say here. And then I say, oh, A. So I'm going to record an A. And then I go back. This is where it's glued. So identify. This point is the same as this point. This is how we see with our math mind. So now we go back again. So you have another A. And then I'm here. And then you do a B. Notice that every time I get out, say, through the little b edge, I come in by the big B edge. But I don't record the big B because I know that once I cross the little b, or afterwards is the big B. So I'm smart and I just record the first one. So this, by going like this, so then A, then capital B, and so on, I get this ring of letters. This is a curve word. This is a different animal than the surface word. So now my surface word is fixed because my surface is fixed. But then every curve or every deformation class of curves can be labeled by a curve word, this ring of letters. This curve word, is reduced in the sense that, well, if I have, if I did say capital B, and then I come here, little b, I'm not going to do small b. So after I do again, capital B, come here. I'm not going to do capital B, small b together, because this is the same as doing this move, and I'm getting a tight representative. I mean, doing this, adding a little piece like this may not change the deformation class, but we want one label per deformation class. So we take the efficient one. No, so the word is reduced. Having A and capital A next to each other is like having +1 and -1 in an equation. They go out. You don't. So we have this curve word, and sometimes I write it as linear word because it's hard to write a cyclic word. So we know that we have a one-to-one correspondence between the deformation classes of these closed oriented curves on a surface and the curve words. So this means that every class is labeled by a unique word, and every word with these characteristics labels a unique class. But now,
is that true? Sorry, you're saying that every surface has a unique word, a unique curve word?
No. Good question. No. First, you have a surface, and a surface has a surface word. Yeah. The surface word might not be unique if you have a very complicated surface, but let's fix the curve word, which is how you cut your surface. The curve word is how you cut your surface. Now that is fixed. Now you draw a curve. And then you are going to follow your curve and see what edges of the cuts it touches. And that will give you the curve word. Any word that you can tell me, say, for this surface we are studying, with A's and B's and capital A's, capital B, any word will label a class of curves.
So I'm sorry, I just didn't understand the graphic. What was the point of the last slide?
So it's just, let me just see. Let's look at it. So I have one particular curve, and I'll show you how to assign a curve word to the class of this curve. But if you have another curve, by this way, you just look at it. Basically, you can do it here. You follow the curve, and you just record what edges you cut. And that will give you the curve word for the class of curves. There are many curves words as...
Many curves that you can put on the surface.
Yes. Yeah, you can go. Yeah, it's infinitely many. This is just one example. Now I'm going backwards is forwards, remember. So now I want to study the crossings of my curves. So first, the self-intersection number of a class is the smallest number of points in which a curve in the class can intersect. So here, for instance, I have some members of the same class of curve, the red curve. What is the self-intersection number of that red curve? 0? I heard 0. 1?
Red blue is the black hole.
Yeah, this is like a hole here, Yeah. So the red curve has self-intersection 1 because I can deform this little, finger that goes here. I can deform it out. So I have one member of this class that intersects exactly once. And well, you have to take my word. You cannot deform it, so it has that you cannot remove by deforming the one crossing. So the self-intersection number of the class of this red curve is 1. And then, sorry, this is driving me nuts. Now, we call a curve simple when it has no crossings. Simple curves is one of the things we study the most. You might have heard about the Poincaré conjecture. It's equivalent to finding a simple curve with certain characteristics in certain, so it's there, one of our shiny objects in mathematics. And of course, if I look at it like this, they look very kind of easy to study, but simple curves can be very complicated. This is a single curve. I can teach you how to do it. It's related to the Fibonacci numbers. This was painted in the Berkeley wall. It was Bill Thurston and my husband, it was many, many years ago. it was the 70s, and students were protesting, and they wanted to paint the wall, and the trustees didn't let them. So they approached, Danny Sullivan and Bill Thurston, who were a little bit famous at that time, and they said, maybe you can paint it. So they couldn't get in trouble. So Thurston was a grad student, and he was studying functions of surfaces. He did this beautiful, amazing theory, and this is a very fantastic example of one of the elements of his theory. So there was a big painting there. A few years ago, they painted over it. I have a picture in my house, but it's no longer there. So this is a simple curve. For instance, if you can paint it and divide the region, the plane in two regions. Okay, so now let's count the crossings. Let's study the crossings. So I'm going to try to look at the word, and looking at the word only, study how many crossings that it has, the class of these curves. So let's look at this point I label in light blue. It's a crossing because, I have this segment and this segment, that two pieces of the curve that cross like this. Now you can look at your word and say, wait, why do I have these two pieces of the curve? Well, what happened? I enter, say, this is like this. At some point I enter through the B. I enter here. I enter through the capital B, came here, and went to the B. So again, if I touch, my curve came here and touched the edge labeled by big B, means like I'm going to have a big B in the label of my curve. Right after that big B, I go again, and there's another big B because I touch it for the second consecutive time. So I have B, B. Same thing here. This arc of my curve is there because my word has A, A. Now, this is independent of what happened with the word. My word could have 1,000,000 letters, but if it has an AA and a big B, there's going to be a crossing because I will have these two segments like this. So this is, if you want to take one picture of my talk, this is it. This is one way that the word, I don't need a surface. I need to know what's a surface word and what's a curved word, and I know there's going to be at least one crossing. In fact, I'm going to have as many crossings as occurrences of AA, BB. So if here I have one AA and a BB, but here I have, another AA and a BB. So this is another crossing. So this is how a computer can count the crossings. Of course, there's so these are the subwords highlighted. It can get a little more complicated. But the idea is just there's a little twist, push forward of what we had before. So in this case, I like to look at this point here. And again, I'm going to look at, oops, oh gosh, I have to go here, this. Now, I look at the two arcs that contain the crossing point. And if you see, there's one, they are both born in the big A edge and go to the small b. And the one goes to the small b, the other goes to the little a. Now, if you look at the words, I don't know whether it's a crossing or not a priori, because they are born in the same edge. So they may cross or not. How can I tell? Well, I look at the past of the curve. So these two, this comes from this and opens up. This here comes from this and like this. So I need to use my arms. The two curves that first we saw, they do this. But if I look at the past, they do this. So, I look at these two pieces of curve. They come from different edges. They go to the same, and in the next stage, they do like this. They have to have a crossing. So when I have words like this is the words here, AAB and big B, AA. This means they are born, because this is different from this. So they're born in different edges. They go to the same. This is the middle A, and then they separate. when they separate, they could do this or they could do this. But the word, again, if you look at the word and the surface word, you can see which one is it. So a computer can and does do it. I mean, I did a lot of my math from that. So I call these subword pairs of subword link pairs. And this is a theorem. It's written in a slightly pedantic language. I managed, okay, oh yeah. But the idea here is a list of subwords that imply intersection. So the theorem says, if you look at a word that labels a deformation class of curves, you can find there certain pairs of subwords so that each pair is going to label each crossing of your curve, if your curve crosses the smallest number of time possibles. So in the same way that one crossing was labeled by AABB, with a little push forward of that idea, each crossing can be labeled by a pair of subwords of your word. And then you can count self-intersections. You can determine which pairs by looking at the surface word. That's why the surface word really contains all the secrets of the surface. In my program, I feed it with the surface word and the curve word. I have it in my website, and you can compute number of crossings. Now let's do some counting. So we can do an easy counting, which is how many words you have in my alphabet is now, let's fix the surface, small a, small b, capital B. How many words, cyclic reduced word, we have of a given number of letters. So if you say 1 letter, I have 4. 2 letters, I have 8. You can count, it's like A, B, B, and then A, B, A, capital B, and so on. Sometimes it's interesting to count non-power words because really if you know that, the non-power, power means like AB is a power, it's AB squared. This is usually the right thing to look at, non-power words. And in this case, the number we have, it grows, like 3 to the word length. Word length is the number of letters divided by word length. Here is the approximation of 3 to the word length divided by word length. And here is the number of non-power words. Of course, that's not very interesting counting. So I did a counting now, starting by number of crossings. So here, this is a table that the computer can do. And in the row, say 2, and column 1, we're going to put how many curve words we have of word length 2, and then label a class of curves of self-intersection number 1. So first we look at just how many you have of a given word length. But now I'm going to organize curve of a given word length by their crossings. How many you have after these crossings. So, so this is the beginning of the table. Here I'm looking at non-power. So here have A, B, capital B. All the curve words of 2 letters have no crossings, label curves with no crossings. We call it like a diagonal of a torus. They go once in the meridian, once in the latitude direction. And so this is a piece of the table. Here is a little bit more of the table. And here is a little bit more. And here is more. And for me, let me just, this table already is like a list of theorems waiting to be proven. So what can you see in this table? What theorem you see? Or 10? What can you say? Any pattern? No patterns? Oh, the green, I don't know if you can see, the greens are zeros. So there's a pattern with the zeros I can help, For instance, that if I look at a certain word length, there are certain curves with a given self-intersection, and then, there's always a curve out to the maximal possible self-intersections, and then there's always zeros. we can also see that, if I look at this is like a curve, well, this curve looks like a parabola. Oh, okay. Shy audience. This is a parabola. In fact, we can prove that the maximal, if you give me the word length, the maximal self-intersection you can have is like the word length squared divided by 4. It's on the nose, a certain polynomial of degree 2. And so here is, to look at it a little better, I made this kind of histogram. So this is a table, and now, well, if it's black, it means there's no curves. This is, for instance, the row of word length 21. The darker the color, the more curves you have. So this tells me that, well, curves of self-intersection 0, I have a very few, and then when I grow the self-intersection up to the middle, I have quite a lot, and then less. So let's look at this. So we want to study that. So here is a histogram of all the words of word length 8 letters. And then I have 16 of self-intersection 0, 24 self-intersection 1, and so on. And then I put a rectangle with a high proportional to how many curves we have in each case. So this is how many you have for word length 8. This is how many you have for word length 20. It looks like something, doesn't it? So these are all the stages, and you see how, quickly it's more and more Gaussian. So this is, I was playing with a computer, and then I saw this Gaussian, and there was this probabilist at the University of Chicago who worked in similar areas, and I wrote an email, and I said, look, I think this distribution of self-intersection, when you sample by word length, is a Gaussian. And he answered, I don't think so. So I sent him this picture, and he answered, let's prove it. And we did. So the statement is that, if you look at all the words of a given word length, and you look at the self-intersection, if you look at these words as curves in a certain surface, then the distribution of self-intersection gets closer and closer to a Gaussian when the word length goes to infinity. Of course, you always have to normalize. Here, the self-intersection, if your word length goes to infinity, the self-intersection always goes to infinity. The self-intersection grows like the word length squared divided by 9 in the case of it's always a constant times the word length squared. In the case of this torus with one boundary component, it's word length squared divided by 9. That's a mean, and the standard deviation is word length cubed times another constant, another rational number. Oops, backwards again. Oh, and this is, I thought I had high school students. Anyway, I'm very proud of this. This is a student that worked with me last year. High school, she was a senior at high school. She's now a freshman at MIT. And she proved the theorem. And so now we're looking at a similar thing. We're making a table, but instead of counting self-intersection, we have always has a fixed surface, and then you fix a certain word. And then you want to organize the curves of a given word length by how many times they intersect your fixed word. So for instance, in the table now, I'm going to have in the row 2 and column 3, how many words that I have word length 2 that have 3 intersections with your fixed word. This is my example fixed word. This theorem works for all words. And I had indication that this worked like the Gaussian. So here is, oops, backwards again. So here is a table. Now you may say, well, this theorem is very similar to the one before. It's not. It's quite different. The counting has to be quite different, and she had to prove it in a totally different way at 17 years old. We'll hear about her soon. So here the distribution is also a Gaussian. Oops. Sorry, I have to not use my. Okay. So I could say something else, so we can do the bagels. Vivian, what are we doing with the bagels?
Whatever you want.
Okay, so let me show you what are we doing. I went a little fast. I could always talk about other things. Maybe let me do a little something first, since I have 5 more minutes. Here is one thing one can do. You can ask what is the number of regions that we discussed in the beginning. Suppose my country now is a Klein bubble, and I want to divide it in regions so that every pair of regions share an edge. So in the Klein bottle, the number is 6. And here it is, crocheted. Each pair of regions touches the other 5. And I'm going to quiz the audience since I have a little extra time. Let's see. You might have done this with your children at school. So here I have a zipper, and I'm going to, there's 2 zips here. I'm going to twist, and I have some Velcro here, and I'm going to attach. Remember, there's 2 twists. So now I'm going to open up the zippers. This is a typical topology problem. What am I going to get? 2 different loops. What length?
Half of the main one.
Half of the.
So it's the double of the main one.
2 double like this. That's not possible because I have 3 pieces, So you see, there's 2 zips.
This is a Mobius strip as it is, right?
Yeah. This is a Mobius strip as it is. Okay. Yes, very good.
Yeah, okay.
So let's see. So I'm open. Huh? Yeah, I should have done the 1 first, but I thought everybody did the 1. I open 1 zipper, and notice that I landed, by going 1, I landed to the other, because when I did the twist, the glue, the pink goes to the purple, so it's a continuous cut now. Ta-da, ta-da. Magic topology.
The small one is a Mobius strip, is that right?
The smallest the Mobius strip, what do you think? Well, huh?
It looks like it is, yeah.
Yeah, because notice what happened. I have my 3 things. The middle, it was just a Mobius strip in the beginning. I just take the band, do a little twist, and reattach. And the outside got together. The outside. Now, what happened if instead of 2 zippers, I have 3? I'm going to put 3, and you can think what happens. I have a seamstress with all the things, and she said, "You gave me a headache." So now I have 3 zippers, and I'm going to twist and attach. What am I going to get? 2 loops. 3 interlock loops. Well, let's use brains and thinking. So notice what's going to happen. The outside, if I continue, now this is glued to this. So there's going to be an outside of my curve. Like if I go, this is, the gentleman said there, this is a Mobius band. The Mobius band has the property that if I go around with my finger, this is a single boundary component. I'm going to go around and come back exactly where you started. So if I glue, the outer edge of the yellow, with the other outer edge, I'm going to come back. So when I open the outside, the Velcro is not very firm. So here it is. Oops. Struggling with. So now I have the red. So the outside, it just gets separated and linked. And now I have a situation, now I have a Mobius band where I can do a single cut. I have 1 more zip. What's going to happen if I cut the Möbius band with one cut in the middle? Huh? It's 1 because now, you know, if you think of the rectangle, the top edge gets attached to the bottom when I twist and glue. So therefore, they are connected. So I get 1. Then, you know, you can make your theorem for what happens with even and odd. Ta-dam. I have this. And in my last minute, I have one more thing I wanted to show. A beautiful, since we've been discussing Möbius bands, what happens when you have two Möbius bands? So the boundary is a circle. It's a single boundary component. So we could attach the circle to the circle with a zip. So here I should have this attached. These are two Möbius, you know, they're slightly fat. But this is a Möbius band here with a single zipper in the boundary. This is another one. So I'm going to attach it. And again, this is something that mathematically I could do. But of course, in this real world, I need more dimensions to do it than one we have. So I'm going to zip it. And I cannot zip it the whole thing because in my limited three-dimensional universe. So what shape am I going to get? It was mentioned before in the talk. Huh? The torus is orientable. And this surface is going to contain a Möbius band, two Möbius bands at least. So this I cannot zip completely, you know, because this is a limited universe. But this is a Klein bottle. You know, a Klein bottle is, you know, gluing two Möbius bands. You know, if you can see, let's see. This is the handle. I have to put a little more inside to see. And sorry, here is a hole. There it is. Handle and the hole, you know, that the bottle has. So you can pass it around. But here is our Klein bottle, the sum of two Möbius bands. And we can do the Bagels later or not. I don't know. I thought we could. But this is what you can do. You can cut the bagel in two pieces like this. So you get two linked pieces. This is what George Hart called a mathematically correct breakfast. And I know it's quite interesting to, you know, it's due to how, you know, the curves are linked on the torus. Okay, I'm done. Yes?
Let's say you have a right-handed man. He just has only one hand.
Okay. Okay.
We walk around the surface.
Uh-huh.
So if he comes around on the other side,
yeah,
as he traverses the whole back of the street,
okay,
is he going to be a right-handed man again or a left-handed man?
Well, the Möbius band sits in our universe.
He's a two-dimensional guy.
Oh. But what does it mean, right-handed in two dimension? I don't even know. It's very hard to define right-handed. It's almost impossible. So, I mean, what do you mean by right-handed?
So just draw a little guy with just one hand, right hand, and then somehow drag him along.
Oh, yeah. Well,
if he comes on the other side.
Right. No, it would change. It's, you know, there's a nice video that Vi Hard made where she's making a picture of a little man moving through she made a Möbius band which is transparent, made of some slide material. And then you see, yeah, he's going to be twisted. Yeah, yeah. If you have a clock, we can think you have a little clock, flat clock, watch, and you move it around, you know, it comes back moving in the other direction. Yes, yes. I'm left-handed. Maybe I should travel in a various van to have a world more adaptive to me, not fighting more with scissors.
Because right and left has to do with up and down. If you're only two-dimensional, there's no.
Any more questions? Or are we going to cut bagels? So let's cut the bagels and thank Moira again.